Thank you so much.
Thank you. Hey, everybody. Good to see you today. So, ever since we've been writing stuff down, we needed to find that stuff. Like, you can go all the way back to ancient Sumer, and the bureaucrats were stamping out the clay tablets about the taxes, and they had to they built indexes on top of those so they could go find the tax records that they were looking for. And in modern times, I need my clicker. In modern times, we have much more modern methods for going and finding the information that we want. So hopefully everybody is familiar with an interface that looks like that. We've all used this. But unfortunately, until very recently, if I put something in there like, I want to watch a good movie, it wasn't actually able to bring me results that were good movies that I would think were good movies, right? Or at least it took a lot of machinery to do that. I could type things like Captain Marvel, and then I would have results that are not Captain Marvel. I don't know what I did with this slide. I'll get Captain Marvel. If I type Captain Marvel, it's a specific query that calls out a particular set of terms, and the search engine in this case is able to match those terms and bring me the right result. Oh, so if I type Captain Marvel, I actually get Captain Marvel. There's my slide. And you can see here I've typed the words Captain Marvel, and again, the search engine is able to take the words Captain Marvel, match them to the titles of those movies, and bring me back Captain Marvel movies, right? So this has brought about an interaction pattern that I'm sure we're all familiar with. You start with a query, you get some search results, maybe you're happy with the search results. Woohoo, win, I go buy the product. Maybe you're not happy. Well, if you're not happy, are you frustrated already with this process? Maybe you leave. If you're not frustrated, you look at your query, you try and think about your query and rewrite your query so that it actually brings you the thing that you want. So this is the information retrieval landscape that we're living in today, right? So I'm going to talk about generative AI and especially how you can use generative AI to solve questions like, I want to watch a good movie, right? And the technology that I'm talking about is OpenSearch. OpenSearch is a search engine, and a search engine is a database technology. You put your data into it, and OpenSearch provides you a rich query capability on top of that data. So much like when I go to Amazon and I type in some words and that search engine brings me products, I can put my data into OpenSearch and I can bring that data back. OpenSearch is a part of the Linux Foundation, so it's fully open source software with open governance, recently moved to the Linux Foundation in September. We have a fairly vibrant project and community behind that project, all working to bring this search technology. So what does OpenSearch do? First thing that OpenSearch does is search. So as we talked about in the past example, you can put in structured text, you can put in unstructured text, and OpenSearch provides you a rich search on top of that. It has adjustable ranking, you can bring personalization into it, it has search suggestions, so if you know type ahead kind of thing, you can implement that, and it supports a faceted search kind of UI. Faceted search is when I have those little guys on the left rail, and I want to click on a brand like Tommy Hilfiger, and then I get only Tommy Hilfiger. So the full search experience is the first workload that OpenSearch supports. Second workload is an analytics workload. A long time ago, I made up this story, by the way. I'm going to tell you the story. It's totally made up, but I'm sure it's true in some way. Somebody was running 10,000 servers, and some error happened somewhere. And they said to themselves, I really wish I had a search engine that I could actually put all this in and I could go find my error, because otherwise I have to go and log into 10,000 servers and grep my logs, right? So OpenSearch really expanded to really capture that workload. OpenSearch supports large volume streaming, log, and event data, and provides you capabilities not only to search that data, but to build analytics on top of that data to understand, my CPUs across my set of hosts are looking like this, and you can draw a line graph in OpenSearch dashboards, which is the UI layer. Now, of course, recently the whole world has gone through upheaval around vectors and generative AI. OpenSearch supports two different kinds of Gen AI workloads. The first of those is bringing semantic information into the search capability. So as we discussed, you're able to capture the meaning of something like, find me a good movie, and you're able to search for that. OpenSearch has broad capabilities for supporting that kind of vector workload. Semantic search, dense vectors, sparse vectors. It scales to billions of vectors and tens of thousands of QPS. It supports a hybrid search mode where you can run both lexical and vector search and blend them together. Many quantization methods that enable you to reduce the dimensionality of vectors to reduce your cost. And then the second kind of workload is as a knowledge base for a generative AI application like a chat application. You use a search engine in a chat application to provide relevant and accurate information that the chatbot is able to then generate text that's more accurate. How does it work? Pretty simple. It's in the databases world, works like a database. It has a REST API, JSON backed. You take your data, your application logs, server logs, or your search data, format it as JSON, send it to OpenSearch. The data is indexed and all of the fields are searchable, so you can build queries on top of all of the JSON fields in your data. And on the query side, it's a REST API, fairly rich, that enables you to build really complex queries and get your data out. So if we look at all of the search loop and how that works, I come with some kind of information goal. And I have this window to put my goal in, which looks like a text box, right? So I can write some text, I can click some facets, maybe I have some geolocation information that helps the search if I want to search near me. All of that information comes in to OpenSearch. Now, the application, you have a pile of information, a bunch of stuff, and you're going to encode that in JSON, send it into OpenSearch, and OpenSearch's job there is to take that query, which is a bunch of text, and geo and facets, and pick the stuff that matches your query, right? So I type Captain Marvel, I want to get Captain Marvel back. OpenSearch's job is to look through all the stuff, find all of Captain Marvel, and then send me out Captain Marvel, right? So how does it do that? And I'm just going to breeze through this, but we have a lexical search capability where we take pieces of text like Miss Kobayashi, Dragon Mane, Toru, cosplay, dress outfit, very soft silicon, vinyl stuffed, cotton, stuffy, right? These are examples. I have a query like cotton washable clothes, okay? So the first thing OpenSearch does, by the way, is analyze that text and break it up into individual words, apply rules like stemming and stop words and synonyms to bring it into common form. You can see things like very, you can see it's got an I on the end. So this is called text analysis. It brings it to a common form. So the first thing it does, cotton washable clothes becomes cotton washable cloth. I then match the words to the words, and I figure out which are the documents that have those words in them. So I take my cotton washable cloth, I have a ranking algorithm that says, okay, the word, which one? The word washable is fairly rare, so I give it a high score. The word cloth is fairly common, so it gets a lower score. I then multiply out to find a score for these two documents, right? And that gives me, in this case, the second one matches. That's lexical search in 2 minutes. Sorry, we can talk after, I can tell you more details. So the new world brings the semantics in, right? So we have a number of different ways that we bring LLMs, large language models, to capture the semantics of pieces of text and match against them. We support, again, sparse models. These are reduced token set large language models that sort of bring you the benefits of token-to-token matching, but with semantics rolled in. Of course, we have multimodal support within OpenSearch where you're searching text and images together. We have hybrid search that I mentioned before where you can run a lexical query, run a semantic query, and merge them together. And we have conversational search capabilities. And this is really, for me, the big change is if we look at that interaction loop, it's starting to expand in time where the things that I type, the things that I search for, the engine is able to keep track of that and maintain a conversational context to bring me better results as I go. So when we work with semantic search, the first thing you do is you take all your pile of stuff and you encode it as vectors. That pulls the semantic information out, send that to OpenSearch. I still have now, on the input side, I still have words and structured information. Images now become a part of what I can use to query. I'm going to generate vectors from this query that are going to represent the intent of my query, and OpenSearch's job is to take that vector encoded intent and find the closest matches and bring those back with ranked stuff that matches my information goal. So fundamentally where we've shifted is, before, words were capturing the semantics as single tokens. Now we're able to build these vectors that capture meaning, semantics, as in a vector space, right? And if you haven't seen anything like this, what an embedding model does is create a multi-dimensional space, and dimensions usually 384, 768, blah, blah, blah. They're just floating point numbers. Like vectors is not magic, it's just like a bunch of floating point numbers, but inside the space you have clusters of related meaning, right? And so documents that are similar are near one another. When I take my query and I encode it, it's going to represent some point in that space. Then I just go find the ones that are closest to that, and that's my nearest neighbor is my search result. We have our neural plugin that helps automate this in OpenSearch. It has connectors to third-party model hosts, and for indexing, either you can yourself take your source document, build chunks out of it, send it off to a third-party model host like Bedrock, and then with an augmented document, send that into OpenSearch in a k-nearest neighbor index. On the search side, it's very similar. You can manually send your query off to like Bedrock to do a vector encoding, and then send that into the nearest neighbor index for retrieval. We have within OpenSearch the neural plugin that automates those pieces where during indexing, you're generating the vector embedding, and during query, you're generating the vector embedding. So we do make it easier to run this loop. Oh, sorry, people were picturing and I went forward, sorry about that. So just to give you a little bit of a flavor of how this works, when you want to send your documents in, you send them through an ingest pipeline. You define this pipeline. You can see here we have a processor that says a text embedding. You pass in a model ID that comes from the external model host, and you just map this field of text, put the vector in this field, okay? So this is with the neural plugin, you send your document through, it ends up in OpenSearch with a vector embedding. On the search side, you use a search pipeline, and in this case, we're doing a hybrid search. We have a bunch of processors. In a hybrid search, remember, we have two clauses. We have a lexical and a semantic. We have a normalization technique. We support a few of these normalization techniques because the score for the lexical and the score for the vector are not in the same scales, right? So you have to normalize the scores before you can blend them. In this case, we use min-max, and then we have a combination technique, taking the arithmetic mean and applying it against those two clauses with weights of 0.3 for the first clause and 0.7 for the second clause, right? And so that's how the whole thing works. I'm going to try to, I have 5 minutes, good. I'm going to try and demo. As you can see, this is an awesome demo. I don't know why it's not coming up. AV help. I pushed the button. Oh, my laptop's sleeping. Well, no wonder it's not coming up. Sorry. Thanks.
It's all good.
Well, it's going to be a shorter demo. Okay, cool. Thank you. So I wrote a little piece of Python that exercises OpenSearch's conversational interface. So OpenSearch does provide an interface that enables you to pull a conversation ID out and then use that ID with subsequent queries. OpenSearch will track the last 5 interactions and use that as part of the prompt to provide a conversation, right? And I'll just give you a little flavor of how that looks. So the first thing we do, we have an OpenSearch client. We do provide clients for, I think, 5 or 6 different languages. We set up our client. It has a host and a port, local host in this case, SSLs. We support SSL, OpenSearch supports SSL, et cetera. We have some settings that we have to put, not very interesting. So here we are creating a connector to the model, right? And this is just a post. It says this is a Bedrock connector. It gives some credentials, and it provides some parameters that go to Bedrock for the embedding, and it provides some actions that happen post sending to Bedrock. So again, just the takeaway there, that's the connector, right? So I said there are connectors to third-party hosts. That's all it is. The next thing we do is we deploy a model. So that connector is going to represent our model. We wire in the connector ID here, and we send that off to OpenSearch. Then we get back a model ID. So that model ID is the model ID we're going to use when we send to OpenSearch. We deploy it. We create a search pipeline. As I said, when we're running this query, right, we are going to run it through multiple clauses potentially. In this case, we're sending our model ID and we're telling where to get the context from that it's going to bring. So then we're going to ingest RAG data. With OpenSearch, the index is the main container. Index is like a database table. Of course, index has associated schema. First thing we want to do is set up the schema. That's called the mapping. And we have a set of properties here. This is data from the Amazon product Q&A data set. It's a public data set. It has a question ID, a title for the question, text of the question. The ASIN is the identifier, the Amazon identifier. It has a bunch of bullet points, a product description, a brand name, right? So this, if you were sending in your data, that you can imagine this is kind of how you would format it. Mostly, it has a set of answers, right? So it's a question and a set of answers, right? And I was going to give you an example of that. No, not that. Oh, crud. I crashed my demo. Where did I do my glasses? Okay, so an example of that, nope. How do I make this thing? Oh, I just scroll it, duh. All right, so here's an example. So in this case, this is a question, is the top flat sheet and the bottom flat sheet something? A bunch of product information on there, things like it's a flat sheet set, it fits mattresses up to whatever. Brand name, product description, brand name, item name, etc. And then a couple of answers, right? So no, mine was not anyways. No, they're separate. No, it's attached. Okay, so then we are going to select a set of sources and load that data in, and then we're just going to Q&A. So let me bring that up. I crashed my demo, so we'll have to run it again. All right, nobody look. Let me do this. You know, it's a demo. It can work right now. Y'all can come up. I'll make the demo work, I promise. Cool. So again, you know, just thinking about, oh, and I wanted to say that I wrote this down. If you go to the OpenSearch booth, we have a few sets of these books. This kind of goes through more or less the content of this talk. Feel free to download. It's also available at O'Reilly. And thank you so much for your time and attention today.